All right, today we're jumping into one of the biggest detective stories in all of science. Seriously. It's a story that has it all: a cosmic crime scene, a 50-year manhunt for a ghost, and a radical new theory with a single, elegant clue that might just solve the entire mystery. So, where do we even begin this investigation?
Well, it begins with a fact that is, frankly, mind-bending. Everything you see, everything you can possibly touch, the stars, the planets, you, me, all of it, that makes up just a measly 5% of the known universe. Yeah, you heard that right. The other 95%, it's a complete mystery. We call it dark matter and dark energy. We know it's there because we can feel its gravity pulling things around, but we have absolutely no idea what it actually is. So welcome to the cosmic crime scene. You see, for the better part of a century, astronomers have been gathering clues, evidence that something is fundamentally wrong with our picture of the universe. The laws of gravity, as we know them, they just don't add up. They don't match what we see at the scene. Our first big clue comes from the way galaxies spin. Back in the day, astronomers like the brilliant Vera Rubin noticed something really weird. Stars way out on the edges of galaxies were moving way too fast. I mean, according to our laws of gravity, they should have just been flung off into deep space. It was as if the entire galaxy was wrapped in this massive, invisible halo of something, holding it all together. And we see this exact same mystery everywhere, in how galaxy clusters move and in the way light itself gets bent by gravity. And look, this isn't some small rounding error. When you tally up all the evidence from the spinning galaxies, the moving clusters, the bending light, you land on this absolutely staggering number. 95% of the cosmos is unaccounted for. We've basically built a model of the universe where we can only explain the very, very tip of the iceberg. Okay, so what do you do? The most obvious suspect for all this missing mass had to be some new, undiscovered particle, right? Something that doesn't interact with light, but has gravity. And that idea, well, it kicked off one of the biggest, longest, and most expensive manhunts in the history of science. I mean, for 5 decades, we have thrown literally everything we have at this problem. We've built these enormous detectors deep underground, miles deep, just waiting for a single dark matter particle to bump into one of our atoms. We've smashed particles together at the Large Hadron Collider at nearly the speed of light, hoping to create one from scratch. And the result of all of this incredible effort? Nothing. Absolutely nothing. The ghost remains a ghost. You know, after banging your head against the wall for 50 years, you start to wonder. And this persistent failure has led some physicists to ask a really radical question, which is summed up perfectly here. What if we've been looking for the wrong thing entirely? What if dark matter isn't a particle at all? What if it's a flaw in our understanding of reality itself? And that question, that's what opens the door to a radical new idea called resonant domain theory, or RDT for short. It tells us to stop hunting for particles and start looking at the problem from a completely different angle. We need to look at the geometry of the universe. Okay, hang on, because this idea is a wild one. The standard view, right, is that we live in one universe, and dark matter is just some weird stuff floating around in it. Resonant domain theory says, nope, that's wrong. It says space-time itself is layered. Think about it like a radio dial. Our universe, all the stuff we can see, is tuned to one frequency, one station. But coexisting in the exact same space are other domains tuned to different frequencies. We can't see them, can't touch them, because they're electromagnetically isolated. But, and here's the kicker, because they all share the same fabric of space-time, we can feel their gravity. Dark matter is just normal matter on a different channel. So here's the key idea that makes this work. In RDT, particles aren't little billiard balls. Instead, picture them as stable vibrations or resonances in the very fabric of reality. It's like striking a tuning fork. The mass of a particle is like the loudness and purity of that note. It's not an inherent property of the fork. It's a measure of how strongly its vibration interacts with the air around it. A more powerful, stable vibration creates a stronger grip on reality, and we perceive that as more mass. And this is a great way to picture it. In this view, a particle isn't just bouncing around randomly. Its path is actively guided by the wave it creates in space, kind of like a surfer riding a wave they generated themselves. The particle and its wave are a single, interconnected system. It's a really fascinating idea that brings back an old concept called pilot wave theory in a new way. Okay, I know this all sounds super abstract and theoretical, but this is where RDT gets really exciting. See, unlike a lot of these grand theories, this one makes a very specific, incredibly daring, and totally testable prediction. It's a single, make-or-break experiment that we can do in a lab right now with tech we already have. And the key to this whole test is this really bizarre, exotic state of matter called a Bose-Einstein condensate, or a BEC. To make one, you take a cloud of atoms and you cool it down to just a tiny fraction of a degree above absolute zero. I mean, the coldest temperature physically possible. And at that point, something incredible happens. The atoms, they stopped acting like individuals. They merge into a single quantum object, a superatom, where thousands of atoms act in perfect unison as one. And this is it. This is the big prediction. If mass is just a measure of a particle's resonant grip on reality, then what happens when thousands of atoms lock together into one perfectly coherent superatom? Well, their collective grip on gravity should change. Specifically, the theory predicts it should get stronger.
This right here, this is the whole ballgame. This is the golden spike, the single make-or-break prediction. Let's look at these graphs. The top one shows the strength of gravity, with temperature getting colder as you move to the left. Now, that gray dotted line, that's what all of current physics predicts. Gravity is constant. It doesn't care about temperature. But the yellow line, that's the RDT prediction. And at the exact moment the atoms become a Bose-Einstein condensate, bam, gravity should suddenly spike, becoming measurably stronger.
I mean, just look at that top graph again. You couldn't get a clearer contrast. One theory predicts a flat, boring, unchanging line, which means gravity is just a fixed background force. The other predicts this dramatic, sudden spike, suggesting gravity is an active participant, tied directly to the quantum state of matter itself. This isn't just a tiny tweak, it's a completely different vision for how gravity works. So, what's the trigger? Why does it happen right then? Well, the bottom graph shows us why. That cyan line represents the quantum coherence of the atoms. As they cross that critical temperature, you see it jump from 0 to 1. That's the moment they've all locked into that single superatom state. RDT says one causes the other. The new collective coherence of the atoms creates a more powerful resonance, a stronger gravitational grip on reality. It's a beautiful, direct link.
And I really want to stress, this is not just some cool animation or a thought experiment. This is a real experiment that physicists can do and are planning to do. It is a direct test of the fundamental nature of gravity and reality itself.
And what's so beautiful about this experiment is how clean it is. There's no ambiguity, no wiggle room. If scientists run the experiment and their very sensitive gravimeter measures a flat line, just like that gray one, then resonant domain theory is wrong. Full stop. Back to the drawing board. But if they see that golden spike, it would mean Newton and Einstein's theories were incomplete. It would mean gravity is not constant but actually depends on the quantum state of matter. And it would mean the solution to dark matter was right under our noses the whole time.
And the best part? We might not have to wait long for an answer. There are multiple world-class facilities right now that can run this exact experiment. Places like the Atom Interferometer at Stanford, or even the Cold Atom Lab floating up there on the International Space Station. The tech is ready to go. The only question left is, what will we find?
You know, a positive result here wouldn't just be a big deal. It would be one of the greatest revolutions in the history of physics. It would mean that for 50 years, we've been on a wild goose chase for a particle that doesn't exist. It would mean the answer wasn't about adding new things to the universe, but about understanding a deeper, hidden geometric structure of the universe itself.
And that just leaves us with this final, really provocative thought. For decades, we've stared out at the heavens looking for the answer to dark matter, searching for tiny signals from distant galaxies. But what if the answer isn't out there at all? What if the key to understanding 95% of our entire universe is waiting to be found right here, in a tiny, supercooled cloud of atoms, just a few billionths of a degree above absolute zero?